It is a pleasure and an honor to be here. Thank you for the introduction for Phil, and Dale. It's always great to be with you. How many of you really are familiar with the rules that apply for things like unlicensed devices, unintentional radiators? Just a quick show of hands. Okay, so thank goodness there's some of you who aren't. For the rest of you, I'll try to make it as painless as possible. So I'm going to talk a little bit about the relevant FCC rule provisions, some of the things that have been going on relative to noise floor activities, and some topics for discussion and observations. So most people, when they think of noise, think about unlicensed devices. We have a set of rules, Part 15, that specifies what you might think of as the EMC requirements, electromagnetic compatibility, for most electronic equipment. It provides for operation of low-power transmitters as well. And there's two basic conditions. You cannot cause harmful interference, and you have to accept whatever interference you receive. So within those rules is this class called incidental radiators. And this is any device that does not deliberately generate RF energy, but does it as a byproduct of its operation. So some examples. Almost everything with an electric motor. Devices that have electrical contacts. The SCR, the light dimmers, that you might not think of as generating noise, but they do. Power lines. The insulators on power lines may not be connected as well as they should be, and you'll have arcings, noise generated. Active antennas. We had a very famous case with, you might say, well, how can an antenna generate noise? Well, we had these active antennas, the little round ones, that were put not only for most consumer use, but in trailer parks, where the electronic circuitry that was used to amplify the weak signal from the antenna went into oscillation and was causing interference to paging systems nearby. And they're really hard to track because they were on trailers. And what they noticed is that in the summertime the interference was up north, and the interference was down in Florida in the winter. So some of our folks were going around knocking on trailer doors, and if you were the owner of one of those mobile homes, you would have been shocked to think that you had anything that was going to cause interference. I have no idea what this thing is on the lower right. This was drawn from some of the older slides we had around, but just to illustrate, things you might not think of as noise generators, sewing machines, vacuums, and so forth. So then we have unintentional radiators. These are things that actually may have an oscillator circuit, a clock circuit for timing. Probably best known examples here, computers, peripherals, even the DVD players, the pads and the MP3 players, the tablets, e-readers, virtually anything with electronics in it generates deliberately some sort of timing signal, and for the microprocessors that are in them, and they generate some noise. So I'm not going to walk you through. Let's see if I can get this thing. No, the pointer's not. So there are generally two classes of devices. One has got a set of radiated limits that are about 10 dB less stringent for products that are going into commercial applications. So they're 10 dB more lenient and than the general devices that might tend to be used anywhere. And you say, well, why? What's the rationale for that? First of all, these rules were adopted more than 30 years ago. And there's a couple of interesting things. First of all, notice that they were based on a separation distance. So when they're not designed to prevent interference from somebody who takes a receiver and it's a meter away from the source. Well, why? Well, perhaps back then we didn't have as much in the way of mobility as we have now. But there was a rationale that it costs money to suppress the emissions. And there's got to be some sort of balance here between what's practical for the devices. And once you start getting that close, at least back then, it was intra-user interference. You might say that's not so much the case now because we have our own products that are operating closer together. So the limits for the general use were based basically on a 3-meter separation, and the commercial a longer separation, thinking that these are going to be machines in offices, they would be separated. The frequency breaks are kind of interesting too, if you look at it. So you had one level that went up to the low end of the FM broadcast band. Then you had another one that went through the FM and the VHF, upper VHF TV band. And then you had another limit that was more lax above 216 megahertz. And then once you got above 960, another flat level. Well, you can argue a little bit that as you went up in frequency, the propagation losses are greater, so the signals don't travel as far, and some rationale for that. But I can also tell you that, so you say, how did you come to these numbers at the time? Well, there was an analysis done by industry, and the dominant concern at the time was TV broadcasting. And it turned out that the analysis for most of the other services, the protection levels were less than what was needed for TV in the majority. So, let's talk a little about digital devices. So this is any device or system that uses timing systems in excess of 100,000 pulses per second, and use digital techniques, including telephone equipment, but exclusive of transmitters. We talked about the two classes, but note that there were big exemptions. So one was for appliances. Another was for transportation vehicles, cars, test equipment, and industrial control systems and others. Well, why? Well, first of all, the industries came back and said, we've been around for years, we haven't bothered anybody, nobody's complaining. We have motors that are generating noise, so why are you worried about the signals from our microprocessor? And it was true, I mean, there really hadn't been any specific instances of interference to report on these. They've been around for a long time. It might surprise you that vehicles back then were a concern. There was a lot of consternation about the ignition systems in automobiles. I still remember in my early days at the lab putting cars on a turntable to measure just how much noise there was from these things. And vehicles got far, far more electronics in them today, but one of the things that helps self-police it is that they can interfere with themselves, so they really try to reduce the noise. So the US wasn't the only place that had these kind of limits. Internationally, there's an organization called CISPR that adopted standards pretty similar to the United States. So when you think about, if you were to think about changing emissions limits, you need to think about, well, this is really a worldwide phenomenon. Today, with all of the international travel and people coming from around the world, you would still have all of these products subject to emissions from these kinds of levels from other countries as well. So let's talk about intentional radiators. Intentional radiators, any device that potentially generates and emits radio frequency energy by radiation or conduction. So the rules for the unlicensed devices specify the frequency bands typically that they can operate in. They limit the power generally to low levels. There are provisions for, in some cases, point-to-point operations at 4 watt CIRP or higher. People often talk about the unlicensed bands. And it's a little bit of a misnomer. There are a handful of bands where these were the bands used, I'll talk about this in a minute, industrial, scientific, and medical equipment. There's actually some allocations for other services in these bands, but the most popular are at 915 megs, at 2.4, and in the 5 gigahertz range. But they're not really, that's where unlicensed is permitted to operate. At these higher power levels, started out with rules, where's Mike? Mike Marcus is in the back. And Mike was leading a spark for the creation of the spread spectrum rules that focused on these bands and led to a lot of the technologies we're using today. The rules just specify limits on either power or signal strength. They don't specify the standards themselves. So often the industry goes off. That's Wi-Fi and Bluetooth. They're all standards developed by the industry. And sometimes they'll develop out-of-band emission standards for their own self-protection that are tighter than what we might have in the FCC rules. And we've got, for most of these, out-of-band emissions limits as well, and limits on spurs and harmonics. So just some examples. Often I'll have people say, gotta do something about those unlicensed devices. And just pull out of your pockets all the things that you have. And there's unlicensed devices, even in the mobile products that we carry around, the Wi-Fi, Bluetooth, and video communications, the card recognition, the RFID, and so forth. So they proliferate basically in every part of our lives, and we carry them. Then there are these restricted bands of operation. Why were certain bands restricted? Typically, these were bands where they were either for safety services or services that are using signals that are extremely weak. And so there were specific prohibitions about deliberately operating in these bands. And there's a list of them. It was hard to keep from having every band listed as a restricted band. And naturally everybody said, well, don't put them in my spot. But these tend to be things like public safety bands, satellite receive bands, and things like that. So let's talk about ISM equipment. Industrial, scientific, and medical. This equipment that generates and uses RF to perform some work other than telecommunications. So some of the historical examples, and this goes back to like 1927. I wasn't there. But it's used for things like dielectric heaters, food tempering equipment, and then what most consumers have, microwave ovens. So how did this get started, this whole idea of ISM bands? And it does go back to like 1927. They were getting interference, I think at the time it was at 27 megahertz or so, from medical diathermy equipment. The doctors were using high-powered RF to treat people, and they were kind of spread all over the spectrum, not just at 27 where they ended up. And so in the United States and the rest of the world, they came up with this idea and said, well, here's what we'll do. Let's carve up slices of the spectrum where we'll keep all of those, and we'll keep it out of the way of everybody else, and we'll let them have unlimited energy in those bands. So the incentive is unlimited, radiate all you want. Well, it worked somewhat. A lot of these systems, there's an emissions limit that's pretty high outside the ISM bands, and for various performance reasons, they operate outside the bands as well. So two new phenomena that we have seen come in the last few years is wireless power transfer. A lot of work going on charging your electric vehicle by radio. And growth of RF light. I'm going to skip through this in the interest of time. Now, the licensed radio services. So, licensed transmitters need energy too, both in band and out of band. There's a kind of rule of thumb out of band limit that we've had, I think, since the beginning of time, and Pierre's done a lot of work on this. That the emission has to be suppressed by 43 plus 10 output power. It works out that it's minus 13 dBm, and I know what the power is because it's proportional. But we've applied more stringent limits in many cases, depending on what's adjacent or where the harmonics fall, and often the industry, particularly through 3GPP, the wireless industry standards are much more strict than this. One of the things that drives this is that today's licensed transmitters have got multiple products in the same device. So they have an incentive to reduce noise so they don't interfere with themselves. But applying these limits has become a lot more complicated. Early in my career, what you did is you turned on a transmitter. It did one thing. It had one modulation format, it was one bandwidth, and you turned it on and you made the measurements and you were done. If you were to pull up, and all this stuff is available, you go into the FCC Equipment Authorization Database and start looking at the test reports for some of this equipment. Not only are they multi-band, but in every band they can have multiple bandwidths. They can have multiple modulation formats, and you start to map it out, and you're doing, how many tests do you do for each one of these things to determine compliance with the out-of-band or spurious emissions level? So it's just not as simple. And I mentioned that the devices include multiple transmitters, so aside from that is, well, which ones can be on at the same time? And so you might think, well, I'll just test one, and then I'll test another, but what if they create in-mod products? So I'm just going to say a little bit about, and I know I'm not doing it justice here, some of the activities on noise floor. There have been some organizations that have focused on noise floor for years. Obviously, the ITU has issued reports that provide information on how you can estimate generally the noise floor for particular environments and particular operating conditions. So ITU publishes reports and recommendations on that. There's a group, I don't know how many of you may have heard of it, called the International Union of Radio Science, or IRSI. They meet about every 3 years, and they have been studying noise as well for as long as I can remember. The National Academy's Committee on Radio Frequencies, or CORE, they're focused primarily on radio astronomy, but they also keep tabs on radio noise, which, by the way, radio noise is often a real key issue for radio astronomy across the board. And then there's others like the ARRL and voluntary standards bodies that do work on suppressing noise. At the FCC, Spectrum Policy Task Force was created, and in 2002 recommended the Commission undertake a systematic study of the noise floor. And actually our Technological Advisory Council started a project to look at the noise floor, and it was funded. The first step in that was to create basically a bibliography, a list of all of the publications, and that's as far as it got. And it's not that folks really didn't care about this. It's just, I think it's symptomatic of the difficulty of trying to get your arms around noise and not only how to measure, but what's the impact. I'll say more about that in a minute. And the Commission has asked about harmful interference and what constitutes harmful interference in many proceedings over the years. I think that's the holy grail of interference control, is a more specific definition of harmful interference. So some food for thought as we go through the day. There's no question the radio spectrum is a critical resource and it should be protected. The current state of radio noise is difficult to get your arms around. There's a lot of anecdotal reports. You'll hear in the hall, oh, did you see at the show when everybody turned on how the noise flow went out? Or we went out and we were doing some measurements and we were really surprised to see a higher noise floor. But there's not, at least that I'm aware of yet, a wealth of information about measurements and scientifically derived tests measuring it. And I think as you went through Bob Atkinson's presentation, you kind of understand that it's just not as simple as you think. You may stick an antenna on a spectrum analyzer and think you know what you're looking at, but all those questions about what kind of detector you're using, do you look at peak, do you look at average, do you look at quasi-peak, what bandwidth, they all make a difference in what you're going to see. I would suggest that it's important to keep it in perspective as well. Radio noise has been rising since the first radio was turned on. This is not really a new phenomenon. So it certainly merits discussion, but I think trying to get our arms around what the levels are today and what's the impact of that. The technologies that have been introduced more recently tend to be more robust. But there are also some pluses and minuses to that. They'll be robust up to a point and then they just go over the edge. So they may be more tolerant of the noise up to a point and then just it's all or nothing. The flip side too, for the digital communications, where when we talked about noise in the past, typically the out-of-band emissions were spikes or narrow-band harmonics. Now the emissions actually tend to fall off with some slope continuously. So it's a little different set of technical characteristics than we had before. So ideally, I think we'd all agree we'd like to see the radio noise be zero, as long as it's applied to somebody else's products. It's really not practical to do that. This is, noise I think is something to be managed. And the real challenge is what's the right balance between noise and noise control and things like the cost and the impact on devices and the viability of meeting those standards. So I could set standards for a laptop here that says I want to reduce the noise down to below the background noise level, and then I'd probably be walking around with a laptop I can't carry. So there has to be some balance. So the costs and benefits, it's really critical to be thinking about this. Let's see, Rob Wolfer out here. Rob would never let anything go out of commission while he was there without cost-benefit analysis. It was more rule of thumb, and Rob was terrific at it. But it's difficult to quantify the cost because there are numerous sources of noise. There's little data on which are the most significant contributors. The scope is a major factor. Are we talking about controlling noise in just one part of the spectrum, or is it all parts of the spectrum? Where is it potentially problematic? And then the cost and the viability meeting, it really depend on what the standards are that are set. And it's difficult to quantify the benefits. So at what point is radio noise harmful interference? This term that we use to say whether something needs to be done. Noise is a combination of natural noise sources, and I don't know that man-made is politically correct anymore. person made. But, you know, and I think Pierre hit the nail on the head. This is, you may not always be able to identify a specific source. So what are reasonable targets for noise levels? If you were to do that, how would it potentially reduce the infrastructure costs that you build, fewer towers, for example? What would the impact be on improved service quality and reliability? I think it's easy to talk about things like dropped calls and so forth, but making a direct connection between that effect and what the causes are is not always so clear. And then can technological solutions mitigate the impact? And so, yeah, there's noise there, but are there solutions that can be built into the systems and the technologies that address it? So some closing thoughts. I think we need to be careful not to leap to conclusions. You know, I'll often hear people say, well, there's lots of noise. You go and put a stronger emissions limit on product X, without really having made the connection between the two. The other thing to think about is your desired signal may be noise to somebody else. So, how many of you are on Wi-Fi? How many of you are generating noise? All of your hands should stay up. So, you know, it's important to keep in mind that these signals that are on the air are often serving a useful purpose. And even within your own service area, you know, your signal doesn't stop at the edge. And yes, you work it out with your neighbors and so forth, but the minute you go on the airwaves, your desired signal can easily be somebody else's noise. We're going to talk about the environmental models, and I'm eager to hear about that, but just I would suggest to think about how well they translate to the radio world. So for environmental, you may have an incentive that says you're going to have some lower costs or assessment if you have reduced a certain type of emissions. When we talk about radio, it's not so clear, because the emissions can be all over the place. They vary with the mode of operation and so forth. And each individual device may have very little impact. And I'm not sure what the incentives would be. So I also agree with Peter that the questions of, well, is there a problem? And if so, what steps, if any, might be appropriate? And so I look forward to the discussion today and a little bit over. Thank you for your attention.